So some of you were asking if the big cell of the Grassmannian has any cluster type. So it does have cluster type in, so cluster type is known for some examples, for some n's and k's. So I will say what those are. So I'm still, so this is just a side note. So here is the table. So this will be my n minus k, and this will be k's. K's are 2, 3, 4, 5. 2, 3, 4, 5, 6, 7. This is A1, A2, A3, A4, A5, 6. Okay, so what this means is n is 3 plus 3, so 6, and if k is 3, then this is of type D4. If n is 7 and k is 3, then this is of type E6, this is of type E8, similarly here. Okay, so in some of the cases, cluster type is known. And that's, is it too small? Okay. Okay, so these are just AIs, A1, A2, A3. This is better? Okay. Okay, now 3, so n is 6, 3 plus 3, and if k is 3, then this is D4. If n is 7, k is 4, then this is E6. This is E8, and so on. Not so on. I don't know after this. So on was the wrong term. If you want to know more cluster types, so let's say, so I will denote by n a maximal unipotent subgroup in the respective groups that I'm going to talk about. So SL3 mod n is of type A1, SL4 mod n is of type A3, SL5 mod n is of type A6, and SP4 mod n is of type B2. I'm not proving this, but I'm just telling you that these are, if you wanted to know more, because some people were asking me what are the types. SL2 is of type A1. Actually, we saw this. The quiver was 1 mutable vertex and 2 frozen vertices. This was the quiver. So forget frozen, we just have A1. Yeah? So we saw this. SL3 is D4. Okay, so I will do one more example. Again, I cannot prove anything in this example. I'm just going to give you a quiver and variables in this case. But there is something that nobody has talked about, so upper cluster algebras. So I will give you the definition of upper cluster algebras. But before that, let me say what the example is, what the quiver is, and then I will tell you more about upper cluster algebra. Okay. And then after that, I will do Grassmannians. Okay, GER-KN, the generalization. Okay, so the maximal nilpotent, I keep saying nilpotent, unipotent subgroup of SLN, subgroup of SLN plus 1C. So this is, so we'll denote this by N. It's the subgroup of upper triangular matrices with diagonal entries equal to 1. Right, so that's the maximal unipotent group. Okay, so again, I'm going to tell you what the quiver is, and then I will have some variables at each vertex. So the quiver in this case, or the initial seed, I should say, is the following. F12, F13, this goes up to F1 n plus 1, and that's the frozen. And you start at F22, but then you stop one earlier, so it's F2n. It's still frozen, so F2n, and then there's an arrow like this. This goes up here, and there's also diagonal arrows, so you keep going until the last one, which is Fn2. Okay, so this is the quiver for unipotent subgroup. The variables are as follows. So again, I think, so we already did this, you will recognize this. Fij, capital Fij is again of a matrix. So suppose G is a matrix in N, then Fij is the largest sub-square matrix whose lower left entry is Ij. So this is same as the earlier example of big cell. And Fij in this case is, you don't have the -1 raised to Mij part, it's just determinant of Fij. Okay, so these are the variables at each vertex. And I is between 1 to n, and j is between 1 to n minus 1. Sorry, n plus 1. Okay, so but this is, so this defines upper cluster algebra on this coordinate ring. So let me write this down. So the coordinate ring on this group has upper cluster algebra structure given by this initial seed. So whose initial seed is the quiver and Fij's. Okay, so this quiver gives the upper cluster structure. What do I mean by that? So I will define upper cluster algebras. Okay. So given a cluster algebra A, sorry. Yeah, okay, this is, right, yeah. Yeah, so you want to stop at some point, so, yeah. So you want to have this condition, yeah. Thank you. Oh, actually, this is what I meant, not one. So this should be, but then that's, yeah, but this is not true. Okay, but this works, so, yeah. Yeah. Okay. Okay, so given an upper cluster, given a cluster algebra A, the upper cluster algebra is defined. Upper cluster algebra is denoted by U and is defined as follows. So you take intersection of Laurent polynomials in x1, so cluster variables, and this intersection is over all clusters x1, x2, xn in A. Okay. So is this okay? So you start with the initial seed. You have some cluster variables. You take x1, x2, but you also take x1 inverse, x2 inverse. Then you mutate, you go to another cluster. You have cluster variables, say x1 prime, x2. So you take x1 prime, x2, x1 prime inverse, x2 inverse, and so on. So you do that for each cluster, and you take, and then you take Laurent polynomials in every such cluster. Then you take intersection, and that's your upper cluster algebra. Okay. This is, so it's known that cluster algebra sits inside upper cluster algebra, and it's not hard to see if you just think about Laurent phenomenon. It's, I think, clear from Lara phenomenon. So because you have, so Lara phenomenon is saying that every cluster variable can be. Yeah, I think it's easy to see even in general. So suppose you have a cluster variable, then Lara phenomenon is saying that it can be written as Lara polynomial in any cluster seed, in any cluster variables in any seed, right? But because this can be written in every seed, it's in the intersection. Yeah. Yeah. Right. Okay. So there are a few cases where it's shown that these two are actually equal. Sometimes it's easy to say, sometimes it's not. But one of the easier things is if A is acyclic, then these two are equal. Okay, so for example, A3 or D3 or so simple cases, or ADE type. So actually, so in example 4, the cluster type, so the cluster structure, so for n equal to, if you set n equal to 3 in example 4, then the cluster structure is of type A3. And so it's not just upper cluster algebra, it is cluster structure. If n is 4 in example 4, then it is of type D4. Okay. Okay, so I will, so this was my last example. So just so you know, so these are not, if you want to read more about, if you want to read about more examples, you can go to Cluster Algebras 2. There are a lot of examples in the appendix. You can, Keller has many, or not many, at least 2 survey papers where he talks about these examples. So you can go read those papers. But in general, the homogeneous coordinate ring on Grassmannians has cluster structure, and this is what I will talk about next. And this is due to Scott. This is Scott's result. But other than just Grassmannians, partial flag varieties, if you know what those are, or Schubert varieties, also have cluster structure, and this is also have cluster structure, and this is due to work of several people. I should add double Brunhasels here too, but okay, so this is due to Bernstein, Fomin, Zelevinsky, which these 3 names you have already heard in several talks, but also by Geis, Leclerc, and Scheuer. I will not talk about this. This is much more involved than what I've been doing. But if you want to read about this, that's something. Okay, any questions? Acyclic, or mutational equivalent to acyclic. There is no classification, but I think that, I mean, I don't know if it's proven that some coordinate ring doesn't have a cluster algebra. Is it? Is there? But is it proven that they don't? Or I don't know. That they cannot have a cluster structure or something. I don't know. Okay. Right. So now I will. So whatever I did for Grassmannian 2n plus 3, there's a generalization of this, which is done by Scott, and that's what I'm going to talk about. So I will not define Grassmannians again because I just did it in last lecture. So, but I will just say it aloud. Grassmannians. So these are k-dimensional subspaces of n-dimensional space. Something in it would look like K cross N matrix with maximal rank, and then they are equivalent. They are equivalent to each other if there is just base change. Yeah. Okay. So as I said, this is a projective variety, and maybe I will show you how you can think about it. So how to see that Kn is a projective variety. For that, we need some functions on Grassmannians, and these are again the Plücker coordinates, but now I will define those for any k instead of just 2. Okay, so need functions on where Kn, and these will be the Plücker coordinates. So let's say I be a k subset of 1 to n. So whenever I write 1 comma n in square bracket, I mean the set 1 to n. Okay, so suppose I is a k subset. So cardinality of I is k. I will use this a lot. Then delta I of a matrix is similar to what delta ij's were earlier. So minor of a matrix with rows I. So k rows of I. Okay, so why is defining Plücker coordinates okay? So replacing, it's again that it has to do with the base change. Replacing A by GA, where G is some matrix in GL KC. All Plücker, so this replacing A by GA scales Plücker coordinates by the same scalar. And hence, we get a map from, so let's see. I want to call Ger Kn as x. Instead of writing Ger Kn, I'm going to write it as x. We get an embedding from x to projective variety nck minus 1. Okay, and this, so a matrix goes to okay, that's the map, and this is called the Fluker embedding. Okay, so image of this embedding is a projective variety. Okay. And is defined by Fluker relations, right? Projective variety is defined by Fluker relations, and there was a question if Fluker relations can be defined for any k. So here are the relations. Okay, so delta, I will tell you what j and all these symbols are. So, but AD, I think, or AC times delta j BD is equal to delta JAB delta JCD plus A, D, and BC. So here J is a subset of this of size k minus 2. And J is disjoint from ABCD. So J does not include ABCD. So it doesn't include any of those. And it's cyclic in 1 to n. Okay, so these are the Fluker relations on GER Kn. Any questions so far? It's okay. Oh, right, yeah, JAC means J union AC. So JAC means J union AC. Yeah, thanks. Okay. Which relation this? That's how these are related. Right, so I mean in 2 cross 2 it was easy to see. If you just write the determinants you will see that, so I think it's similar to that. I mean it's just the K version of this, the K version of that. Right. Yeah. Yeah, and that's why, yeah, that's why it's J is just constant everywhere, so you can get rid of and then see exactly this relation. Any other questions? Okay, and so by transfer of structure in this map, you can see that X is a, I will just write this by okay, and then the homogeneous coordinate ring is defined by C with all these deltas, delta I, where I is a K subset of N, or 1 to N, and then mod by the Plücker relations. Okay, so I just mean mod by this idea. Okay, so I want to show you guys that this is this homogeneous, but I'm not going to show exactly, I'm not going to give a proof, but I will tell you how to get quivers to show that, to get a cluster structure on this. And to do that, I will have to define certain diagrams and stuff, so let me do that. So this will take a while, but until we get to quiver. But it's a nice combinatorial. These diagrams are used in many places in combinatorics, not just cluster algebras. So these are very interesting objects. So these were defined by Postnikov. So these are Postnikov diagrams, and to start with, I will need, so let C be a circular graph with n vertices. So set of vertices we will call by C naught, and these are n numbers, so 1 to n. And then edges, C1, there are also n edges because it's a circular graph. So for example, let's do 5. 1, 2, 3, 4, 5, 6. So these are my vertices, 1, 2, 3, 4, 5, 6. And the edges are, they go from I to I minus 1 to I, sorry. So this will be edge 2, this is 3, this is 4, this is 5, this is 6. Okay, so edges go from, so ith edge goes from I minus 1 to I. Okay, so 2 goes from 1 to 2. I mean, not directed, but yeah, mod 6. Yes, everything is mod n after this. I don't want to write this everywhere because it gets a lot, so. What's that? Yeah, I mean, there are ways of doing this. People do different things, but yeah. Okay, and now a Kn Postnikov diagram is defined as follows. So there are several ingredients to this. One is, okay, so this, we will call this D. It consists of n strands, okay, which go from, so these are just curves. I will give you example in a few minutes, but let me just write everything down. Okay, so these are n strands in a disk. With n marked points. And our n marked points are going to be these on the circular graph. And the strands go from, the strand I goes from I to I plus k. So this k comes from here. So Kn Postnikov diagram will be associated to GR Kn. So that's the k. So these diagrams have to follow certain axioms. So local and global. There are three local axioms. I'll write some of them here. Okay, so local axioms, there are three of those. Let's call it A1. Only two strands cross at a point. All crossings are transverse. Second local axiom is there are finitely many crossing points. And A3 is, I will tell you what this means. Writing this is, so this sounds difficult than what it is, but proceeding along a strand, other strands crossing this one alternate between right and left. So they either, so if one of them comes from left to right, then the next one should come from right to left. Okay, so what this means is, let me show you here. So suppose here is a strand. Then, so if there is a strand coming from here, which is directed like this, then the next strand cannot pass in this direction. It has to, the direction has to be this. Okay, that's all. Okay, and now for the global axioms, there are two of them. B1 is there are no self-intersections. So a strand cannot intersect itself. And then B2 is if two strands cross at 2 points, if two strands cross at two distinct points, u and v, such that u is not equal to v, then both of them should be directed opposite to each other. So one strand is oriented from u to v, so is one strand is from u to v, and other is from v to u. So suppose this is u and v. So if a one strand is going from u to v, then the other one has to go from v to u. Okay, and we always consider these up to some moves. So consider these up to isotopy and twisting, untwisting moves. Twisting, untwisting moves. So just to give an example, suppose two strands, suppose this is one strand, then this is same as oriented differently, correct. And so if these are same as, you can just stretch in them, and then, this is same as that. You don't have to, you get the point, right? You can straighten them, and then they're the same. Yeah. No, I don't think so. I think if there is a vertex in the middle, then you cannot do that. Oh, other strands going on. Yeah, then it's still fine. Yeah. Yeah, then you cannot do that. Right. So I mean vertex of the quiver, which will be dual to this. But yeah, if there is a crossing in the middle, then you cannot. But as long as there is nothing in between, it's fine. All right, and then twisting, untwisting is the following. So, this is true even at the boundary. So if you have something like this, and then I'll get the then you can just have this as coming in, going out and coming in. So this is a boundary vertex. Is it? Yeah.
Your picture, it should be perhaps the mirror image of this. Showing as if a strand is going from bigger number to smaller number.
I mean, they can move around. So. Yeah. There can be a strand. If there is a strand from, so there will be a strand from 2 to 5, and then there will also be a strand from 5 to 2, for example. Mod n. Yeah, everything is mod n after this. K is this, yeah, K can be anything less than n, yeah. So what was the question, Lauren's question? Oh, so you mean this should go out? I see. So here this should be still that. Yeah. Okay, yeah, great. Oh, did I not? I'm very. This picture. But I thought I just did. No?
No, you didn't.
I did not?
No.
The way they see the flow of the erosion on the right, the most right point, the flow of the erosion of the same direction.
Okay, so you're saying this flow should continue here. Okay, I understand. Okay, I understand. Yeah. Is this clear? No? What is not clear? So what I'm saying is, I will show this an example, but what I'm saying that if you have something like this in your diagram, you can just replace that with this. And if you have something like this in the diagram, you can replace it with this. And I had the directions wrong because that's a good point, because whatever, so I'm just twisting this locally here. I cannot change the directions here. Okay, so that was the issue. Okay, so I will give you an example now. So this is not the quiver, right? This is just the Postnikov diagram. This is just the strand diagram. And here is an example for k equal to 3, n equal to 6. And I learned this technique of drawing. So in general, drawing strands is not the easiest thing you could do. But I learned this technique from Robert Marsh, so I'm just going to follow what he did. So instead of drawing continuous curves, I'm going to draw them in triangles and squares so that it's easy for everyone to follow what's going on. So I'll start with a hexagon. I'm going to draw these triangles on each side of the hexagon. Then on the alternate sides of, or like this, I'm going to complete these rhombi. But I won't do this here. Now I will do this here. And then I'm going to draw 2 more triangles on each of these sides. So here. Okay, and this is somehow is going to give us, and that's it. And this is somehow is going to give us the strand diagram for GER36, and this was secretly sitting inside a disk. Okay, so let's. What I'm doing is, so I started with the circular graph with 6 points. So these are my 6 points. 1, 2, 3, 4, 5, and 6. Let's go back to the definition. Postnikov diagram consists of n strands on a disk, right, or in a disk. So those are, I will tell you what the strands are, and they're going to go from I to I plus k. So my k is 3. So my strand I goes from I to I plus k, I plus 3. Okay, so for example, strand 1 should go to 1 to 4. Let me orient each of these strands or these edges. So if I orient to one of those, it's enough. Okay, so the strands are, okay, so I want to go. So this should come from here. This orientation is so that I get a strand. I will explain in a minute. But yeah. Okay. The rhombus should not be oriented. Is that? This one? Right, so this. Yeah. So maybe. Yeah, this should be. Maybe this is wrong. Great. Thanks. Okay, so, huh? Yeah, so that's a good question, but I think so this is a made-up process of drawing strands. So let me tell you what the right way should be. So the right way is you started, so let's take 3, okay? So you start at 3, and then, so this is the real strand. Okay, can you see the yellow part? So I'm saying this is the strand. I just drew the way I drew it to make the life easy for us. Make it. Do you understand? So that everyone can follow how I'm drawing it. That's all. But the real strand goes like this. Okay. So So 3 goes from 3 to 6. So this is strand number 3, the yellow one. Let's see. Suppose I start at 2. So 2 should go to 5, and the pink one is that, and so on. I can draw more, but let's see. I might need 1, so I will draw 1. So 1 goes to 4, and the orange one is that. Okay. And now, I mean, you can see the other one. So 6 should go to 3, so this goes like that. Okay? Any questions? Yeah, but I mean, if you follow the axioms, it's, I mean, you can get it not easily, but you know, if you follow the axioms, there is less ambiguity. For a permutation, yes. So like for, yeah. Up to moves that I will tell you, but yeah. So will I tell you about this? I think I will. Yeah. Okay. Any other questions? So again, this is not a quiver. This is just a strand diagram. And now I will label the regions. So there are 3 types of regions in this diagram. So label. So okay, so we label only certain regions. So let me tell you about 3 kinds of regions. There are 3 kinds of regions. Some are oriented clockwise, some are oriented anti-clockwise, and some are not oriented. Some are alternating. So in this case, both oriented clockwise or anti-clockwise are triangles, but they don't have to be triangles always. In this example, they're triangles. And alternating are rhombi or hexagon. And boundary regions. So boundary regions don't have a shape, but they're alternating. So we will label only unoriented or alternating regions. So we will label these 3 regions. So let's see. So labeling is a little involved. So label alternating regions by with strands passing to right. So or it's easier to say the other way. If I'm going if I'm going on this strand, if I'm traveling on this strand, the region on the left gets a 3. Okay, so the region So this region will have a 3. If I'm traveling, so let's say 1, then this region is on the left, so it will have a 1. And then, let's see, if I'm traveling from 5 to 2, so I'm traveling this strand, then this region is on the left. So the label of this region is 135. What's that? They are labeled. Yeah, yeah. Okay, so for example, so let's say 5, all regions on left of 5 will get 5. So this will get 5, this will also get 5, this will get 5, and so on. So I will just label all of them now. I won't keep saying this, but this is 3, 4, 5. This is 4, 5, 6. All the boundary regions will be consecutive numbers up to mod. Okay, so 1, 5, 6. This is 1, 2, 6. That's 1, 2, 3. This should be 2, 2, 3, 4, and so on. This is 1, 3, 4. This one is 1, 2, 5. Yeah, that was just an example. This has 3, 5, 6. Sorry. 6. Yeah. Okay. So now, after labeling, finally, we can. So this labeling gives vertices in the quiver. Yeah. Is the same, yeah.
Whenever you find it on the left,
you have that number in that region. So 5 is this strand. So it's on the left side of this. So every region here is going to get 5. Okay, any questions? Okay, and then, so these labels, so these alternating regions are going to be vertices in the quiver. So vertices, or let me write this more clearly. So to get a quiver, vertices in the quiver are going to be the labeled regions or the alternate regions. And for arrows, you follow the following rule. So suppose you have 2 strands. Suppose you have 2 crossing strands like these, then this is probably not visible. Then you go, so that if there is a vertex here, then you go, it's directed like this. So you go with the flow of the strands. Okay, so both of these strands are going up, so your arrow is going up. Okay, so let me draw the quiver here. Maybe I will use blue color. So because these 2 strands are traveling to the right, from left to right, this is the arrow. I will do all of this. And of course, if there is no intersection of strands, there won't be an arrow. Is this okay? Everyone? No? Maybe I can do a smaller example and it will be more clear because there is so many things going on in this picture. but let me finish this one. Okay, I think I've drawn all the arrows. No, I haven't. Yeah, okay. Yeah. Anything else? Okay. Yeah, so here, so let's, here, oh yeah. Okay, so see, these two strands are traveling here, and so this one is going in this direction, this one is going in this direction. So together they're flowing down, so the direction is this. Okay. So both of these strands are going in this direction, so your arrow is going in that direction. Okay, so this is how we get the quiver. Yeah. Right. Yeah. Only adjacent, or by adjacent I mean the one that have common point. Yeah. Sorry, can you say that? Resultant vector? Yeah, like the general flow of strands, I guess. There are some rules. I mean, I think if you mutate, it's going to be the same. It will have the same. Let me say this. Oh. Oh, I thought he asked about the strand diagram and not the direction. So the direction is fixed. Like you have to have a strand from 3 to 6. Now how you draw it depends on all other strands that are going to, I mean, all other strands are going to play a part because you have to follow all these axioms. Oh, it's okay. Well, no. I mean, you can have something like, that goes like this, but up to homotopy or isotopy or whatever is the same thing. Yeah. Is that what you asked? So there cannot be two arrows, but there can be a two cycle, like a cycle, two. Then you remove that. And then, yeah, maybe I can, I'm out of time. I don't know, maybe I can show how, very quickly how, or no, I think that's a part of next example. Yeah, I will just do next example tomorrow. I will stop here. I will say something more about this quiver in the next class. I won't draw the whole thing, but let me say one thing because I have this here. So again, the boundary regions correspond to frozen variables. So the only non-frozens we have are these: 1, 3, 4, 1, 3, 5, 3, 5, 6, and 1, 2, 5. Only these are mutable. And then if you look at the quiver, it's like this, which is D4. Okay, so this cluster algebra is of type D4. But yeah, anyway, I will stop here. So you are not allowed to mutate at the hexagon because that won't be a Postnikov diagram.
So Postnikov diagram is from one seed or for the
I think it will give you only one seed.
Okay, so it's for one seed.
Right, exactly. Yeah, only one seed, yeah. Yeah, right, exactly, yeah. There is a notion of mutation, but again, as I said, you cannot mutate at the hexagon. If you mutate at the rhombi, then you can do things. Because if you mutate at the hexagon, the quiver gets very messy. So there is no good way of doing it. Right, yeah, I think that's right. Yes, yeah.
Does this particular quiver, does this have anything to do with Mercedes-Benz?
To what? Sorry.
With Mercedes-Benz? Because the quiver very much looks like the Mercedes-Benz.
Oh, no. I think it's just a coincidence.
I was thinking whether it is a Mercedes-Benz quiver or